students, welcome to 60 out of 60 in KCET Chemistry 2025 series just in 200 days. So yes, now as you all know, we are doing everyday classes. So we have completed all the 3 chapters of physical chemistry, that is solutions, electrochemistry and chemical kinetics. So all these 3 chapters are very important and high weightage topics because you can easily expect 3 to 5 questions from these chapters, right? So yes, now it is time to revise these chapters. Revision is very important. Revision is the key for retention, right? So every time when we complete a certain set of chapters, we need to revise, we need to write a test so that we can understand that whether we have remembered everything from these chapters or not, whether we are able to solve the questions or not, whether we are able to apply the formulas or not. So it is very important to revise these chapters. So yes, to help you with this revision, today I have come up with the class 10 of this series where we are going to discuss or where we are going to revise the entire physical chemistry of PU2, which includes these 3 chapters, that is solutions, electrochemistry and chemical kinetics. Okay, so yes, here you can find all the formulas, all the concepts that we have discussed. Everything is available in this particular lecture. Okay, so now I'll request all of you to join our WhatsApp channel. The link of the WhatsApp channel will be there in the description section, so you can get all the notes, all the questions, solutions, everything will be available in our WhatsApp channel. So please join our WhatsApp channel so that you do not miss out on any important notes. Okay, so yes, now I want all of you to sit with a pen and a notebook and to write down all the formulas once again, to revise, to recapitulate and to recall all these formulas and important concepts also you can note down. Okay, so yes, now please sit down, please let us get started. Okay, the first one I'll be telling you as I make every time how to start this revision. So yes, in this revision we are going to cover 3 important chapters, that is your solutions. So yes, now I'll tell you how are we going to proceed in this lecture. So first, in physical chemistry we'll be covering 3 important chapters today, that is solutions, electrochemistry and chemical kinetics. Then in solutions, what all things we are going to cover? In solutions we are going to cover types of solutions, concentration terms, Henry's law and Roult's law, ideal and non-ideal solutions, colligative properties and abnormal molar mass. So there are 6 topics under solutions chapter. Remember that we are going to cover all the 6 topics. Now coming to electrochemistry, so here first topic is galvanic cell, then we are going to discuss Nernst equation, then electrolytic cell, then products of electrolysis, then conductance of electrolytes, and then lastly we will talk about batteries also. Okay, now coming to third chapter, that is chemical kinetics. Here first we will go types of rates, then we will cover factors affecting rate, then we will discuss effect of concentration in detail, which is the major part from where questions have been asked. Then we will discuss effect of temperature, then we will discuss effect of catalyst, and lastly we will just see what is collision theory and its postulates. Okay, so yes, so these are, so you can see total 6 plus 6 plus 6, so we have total 18 topics including all the 3 chapters. We are going to cover each one of them in a quick revision mode so that you can recapitulate, recall all the formulas. Okay, so yes, now let's get started. So why we are doing this? So first of all, you need to understand that in your KCET examination from PU2 physical chemistry alone, you can expect 10 to 15 questions. Okay, so like that is almost there are total 1/4, or you can say 25%, 15 questions we can expect from PU2 physical chemistry itself, right? And these topics are very easy, very scoring, and you just need to remember certain formulas. Very easily you can get this 15 marks, okay, 10 to 15 marks. So that is why this is very important to revise. So the chapters here are solutions, electrochemistry and chemical kinetics, which are very most important chapters for your KCET examination. We cannot afford to miss these chapters. Okay, so yes, now we have understood what is the weightage, why we should do it. So there are, I'll tell you very important thing is why we have to cover physical chemistry. The first point here I'll tell is you get very sure questions. You know what type of questions will be asked. Okay, the questions are very predictable questions are there. Okay, then I can say, and you do not have any exceptions, no exceptions here. Exceptions are not there. You do not have to remember anything specific, so just you need to remember the formulas and apply them directly. Okay, no very twisted questions are also not there. Remember formula and apply, right? So that is why So these are the reasons that is why you must cover, that is why you must cover physical chemistry, these 3 chapters. Okay, that is what you must do so that you can assure that 10 to 15 marks for your exam. Okay, fine. Let us start with the part 1, that is solutions. Here we are, as I told you, we are going to discuss types of solution, then we are going to discuss concentration terms, Henry's laws and Roult's law, ideal solutions and non-ideal solutions, colligative properties, abnormal molar mass. Then in concentration terms, we are discussing mass percentage, volume percentage, mass by volume, parts per million, then molarity and then molality, right? Molality. And then coming to mole fraction also. Next, if you see, we are going to cover ideal and non-ideal solutions. Here positive deviation, negative deviation and azeotropes. Then in colligative properties, the major part from where questions have been asked, that is your colligative property. Here we will be discussing the relative lowering of vapor pressure, elevation in boiling point, depression in freezing point and osmosis. Okay, so you can see now we are going to cover all these topics from solutions chapter in this particular lecture. Okay, so first, types of solution I will tell you based on the physical state of the solvent. So how is this types of solution? Based on the physical state of solvent. Based on the physical state of solvent. So if solvent is solid state, then we call it solid solutions. If the solvent is in liquid state, we call it liquid solutions, and if the solvent is in gaseous state, we call it gas solutions, right? So now you can see solute particles are there, gas in gas, liquid in gas, solid in gas, then liquid solutions, gas in liquid, liquid in liquid, solid in liquid, solid solutions, gas in solid, liquid in solid and solid in solid, right? So you need to know certain examples for this, and just you have to know certain types of solutions based on the solvent and their examples. That's it, it will complete this chapter, like completes this topic. Okay, yes. Now coming to concentration terms, we can just discuss all this concentration. First is mass percentage. Mass percentage means the mass of the component by the total mass of the component, the total mass of the solution into 100. Okay, I'll tell you an example for this. Like for example, I tell that it is 10% HCl, mass percentage we represent W by W. Okay, what does that mean? That means 10 gram of HCl, okay, in 100 gram of solution. So what is the mass of the solvent here? If you see 100 gram is solution, 10 gram is solute. So solvent will be 100 minus 10, that is 90 grams. So solvent mass will be 90 grams. Okay, now coming to volume percentage of the component. In volume percentage, volume of the component in the solution by the total volume of the solution into 100. Now here if I say that 10% HCl V by V. Okay, so that means 10 ml of HCl, 10 ml of HCl in 100 ml of solution. Okay, so now if this is the case, solute is 10 ml, solution is 100 ml, solvent will be 90 ml, right? Now coming to the next one, mass by volume percentage. Okay, so if you see mass by volume percentage, that means mass of the component by the total volume of the solution into 100. So if I write 10% HCl W by V, that means 10 gram of HCl, okay, is present in 10 gram of HCl in 100 ml of solution. Getting? So 10 gram of HCl in 100 ml of solution. So that is what given by mass by volume percentage. Okay. So now coming to the next one, parts per million. So this is used to calculate very trace amounts of concentration. So number of parts of the component by the total number of components into 10 to the power of 6. Okay. Now coming to mole fraction number of moles of the component by total number of components. So here suppose I have just a minute. Yeah, suppose I have two components A and B. There is a mixture. Okay, I have component A and I have component B. Number of moles of A is Na, number of moles of B is Nb. So if I want to calculate, so this is if I want to calculate mole fraction of A, that will be number of moles of A by number of moles of A plus number of moles of B, right? So now XA, another relation you have to remember, XA plus XB is equal to 1. Okay, so the total mole fraction is always equal to 1. So if there are 3 components, then XA plus XB plus XC will be equal to 1. Clear? Okay, now coming to the most important formulas, that is molarity and molality. So molarity is denoted by capital M. Okay, and what is the formula here? Moles of the solute by volume of the solution in ml into 1000. Now for moles of the solute, I can write given mass by molar mass into 1000 by volume of solution in ml. Okay, now suppose I write that a solution 2 molar HCl. What does it mean? It means 2 moles of HCl in 1 liter of solution. 2 moles of HCl in 1 liter of solution. Okay, now molality is what? Number of moles of solute by mass of the solvent into 1000. Okay, now number of moles of solute is given mass by molar mass into 1000 by mass of the solvent. Now suppose if I write 2, first molality is denoted by small m. If I write 2m, that means 2 moles, so I'll write 2 mole HCl. That means 2 moles of HCl, okay, in 1 kg, or I can say 1000 gram of solvent. Okay, so here it is 1 liter, or I can say 1000 ml. Getting? So these are the meanings of the different concentration terms. You need to be very clear with these terms. Okay, so if like for example a question is given 5 capital M, 5 molarity, that means you should understand that 5 moles are present. Okay, so like this you have to understand the physical meaning of concentration term, not only the formulas. Clear? Okay, now let us move to the next one, that is Henry's law. So Henry's law, what does it tell? I'll just explain this. Henry's law, it tells that solubility of a gas, okay, in liquid is proportional to the partial pressure of gas above the liquid. Okay, so we get that X of the gas is nothing but solubility, P of the gas is nothing but the pressure, partial pressure of the gas. So partial pressure of the gas is equal to Kh into mole fraction of the gas. So what is this one? P of the gas is partial pressure, okay, of gas. Next, what is Kh? Kh is nothing but Henry's constant, okay, Henry's constant, and this one is mole fraction of gas. Okay, now this mole fraction we can tell that it is solubility. Clear? Getting? Now coming to here, one more important thing, that Kh is inversely proportional to X of the gas, or I can say Kh is inversely proportional to solubility. Clear? Getting this one? Okay. Now coming to Roult's law. So what does Roult's law tell? Roult's law is also very similar to the your Henry's law, but according to Roult's law, I can say that, okay, the solubility of a gas, okay, in a liquid, sorry, one second, okay, so now coming to Roult's law, that Roult's law state that in a solution of 2 volatile liquid, in a solution of 2 volatile liquids, okay, the partial pressure of each component is proportional to its mole fraction in the solution. Okay, so now I'll explain you with a diagram here. See, suppose we have a container like this. Okay, we have a container like this, and here I have gases A. There is some gas A. Okay, sorry, there is no gas here. There is one component A which is volatile. Volatile means it can vaporize. Okay, and I have another component B here. Okay, so let me take another component B here, which will also, volatile means it can also vaporize, and we have a closed container. So what I'll get vapors of A here. Okay, we'll get vapors of A. Vapors of A will be produced, and at the same time vapors of B will also be produced. Right, vapors of A will also be produced, vapors of B will also be produced. So this vapors of A which is produced here, we call it as partial pressure of A, and these vapors of B which is produced here, we call it as partial pressure of B. Right, PA is there, PB is there. Now the Roult's law says that the PA is proportional to the mole fraction of A in the liquid. So I can say that PA is proportional to XA and PB is proportional to XB. Right, now to remove the proportionality, we can multiply a constant. So I can say that PA is equal to P naught AXA and PB will be equal to P naught B XB. Right, so now what is the total pressure here? P total will be equal to PA plus PB. So I can substitute P naught AXA plus P naught B XB. So I'll get this equation. Clear? I hope I have explained these all concepts also in Henry's law in detail. Okay, now coming to the next one, ideal and non-ideal solutions. So ideal and non-ideal solutions, just you need to know the difference here. Ideal solution obeys the Roult's law. This does not obey the Roult's law. Now what do you mean by obey the Roult's law? Obey the Roult's law means in this case total pressure will be equal to P01 x1 plus P02 x2 in a mixture of two components. Okay, like suppose you have taken two components A and B or 1 and 2, two volatile liquids are there and the vapor pressure here is there. The total vapor pressure will be equal to this one. Okay, so in that case we call it as it obeys the Roult's law. So now what happens here is when X, like you have two components 1 and 2, right, both are evaporating. So if the interaction between them is very weak, so the first statement is saying that the interaction is very weak, that means A and B are not binding with each other, they are not happily staying with each other, they both want to escape from each other. So more A will evaporate, more B will evaporate, vapor pressure created will be higher. That is why P total is more. Here what happens, interactions are stronger, that means A and B wants to be friends, they want to stay with each other. So that means less A will evaporate, less B will evaporate, and the total pressure will be less here. Okay, next coming to delta H mix is greater than 0, here delta H mix will be less than 0. Okay, so okay, this point we have given by mistake, that is not required. Examples you should remember, ethanol and acetone, CS2 and acetone, these are your positive deviations, and phenol and aniline and chloroform and acetone, these are your examples for negative deviation. Okay, so now we can see the graph for positive and negative deviation. So you can see in positive deviation the P total increases from the ideal value, in negative deviation the P total decreases from the ideal value. Okay, fine. Now coming to azeotropes. Now azeotropes is a special type of solutions. Okay, here some points regarding azeotropes. So first of all, azeotropes are binary mixture. Binary mixture means there will be having two solutions or two components in a solution. Now they have the same composition in the liquid and the vapor phase. The mole fraction or the solubility in the liquid phase and in the vapor phase are same. Now what is next? And they boil at a constant temperature. Okay, so if you have two components A and B, they will have their separate boiling points, but once they become azeotrope, they both will boil at the same point. Okay, they will have a common boiling point where both will boil at a constant temperature. Now in such case it is not possible to separate the components by fractional distillation. If you know fractional distillation, what is the theory behind it, that two components who have very small difference in their boiling point, they boil, we allow them to boil. So the one which is having low boiling point will boil first, and the one which is having higher boiling point will boil later, and then we can separate. But here, because they both have the same boiling point, we cannot separate them on the basis of fractional distillation. Okay, so what are the points regarding azeotropes we remembered? First is it is a binary mixture. Second, that they have the same composition in the liquid phase and in the vapor phase. Third is they have they cannot be they boil at a constant temperature, and the fourth is because of this they cannot be separated using fractional distillation. Okay, now azeotropes are again of two types, minimum boiling azeotropes and maximum boiling azeotropes, which we will see in our next slide. So maximum boiling azeotrope means here the boiling point is more than the boiling point of the individual components. Okay, what is the meaning of this one? Boiling point is greater than the boiling point of individual components. Okay, so this is shown by negative deviation. So now you can understand negative deviation means the attractions were very stronger, right? If the attractions are very strong, we need to heat them more to boil them or to separate them. That is why the boiling point increases here. Now if you see minimum boiling azeotrope, it is by the shows positive deviation. So here what happens, what I can tell, that the boiling point is lower than the boiling point of individual solutions. Okay, boiling point is lower than the boiling point of individual solutions. So here what happens, again if you see this minimum boiling azeotrope, positive deviation means the solutions are not, the two components are not interacting with each other, so they do not have any strong force of attraction, we can easily boil them. If we can easily boil them, so the boiling point will decrease, so that is the minimum boiling point azeotrope. Here examples you can remember, maximum boiling azeotrope nitric acid and water, and for minimum boiling azeotrope it is ethanol and water. The composition 68:32, here it is 95%. Okay, so that is all about azeotropes. Now coming to the next important point, that is your colligative properties. So colligative properties very important, and from where most of the questions have been asked. So first colligative property is relative lowering of vapor pressure. So the formula for is delta P by P. So P naught by, okay, P naught minus P by P naught is equal to XB, Na by Na plus Nb. So what is this delta P? Delta P is the change in the pressure. So what is P naught? Pressure of pure solution, right? What is P? Pressure of solution. So I'll write this one, pressure of pure solvent. Okay, so one second. So this is pressure of solvent, pure solvent, and this is pressure of solution. Again P naught is this one. XB is what? Mole fraction of the solute. Mole fraction of solute. Now mole fraction we can give as Nb by Na plus Nb. Okay. Now if the solutions are very dilute solutions, in that case what happens, in dilute solutions we consider that number of moles of solute is very less than number of moles of solvent. So we can ignore this Nb and the final equation becomes like this. Clear? So generally we need to use this formula while solving questions. Now the next colligative property is elevation in boiling point. So when you add a solute, the boiling point increases. Okay. So now formula for that is delta Tb is equal to Kbm. Now what is delta Tb here? Delta Tb is Tb minus T naught B. What is Tb? Tb is the boiling point of solution because it is increased boiling point, and T naught B is the boiling point of pure solvent. Okay, got this one. Next Kb, then we have Kb. Kb is what? Kb is your elevation constant. Elevation constant. Okay, now M here stands for molality. Okay, so this I have expanded the formula of molality, that is W2 by W2 by M2 into 1000 by M1. So what is M1 here? Mass of solvent. Mass of solvent, right? What is W2? Mass of solute. M2 molar mass of solute, right? This is molality formula. I think everyone would be knowing it. Okay, now coming to the next one, that is depression in freezing point. So in depression in freezing point, we have the formula same, delta TF is equal to KF into M. So when a solute is added to a pure solvent, its freezing point decreases. Okay, so how I can write this delta TF formula? So now see, delta TF will be equal to, okay, T naught F minus TF. Okay, if you remember in boiling point it was TB minus T naught B, but here it will be T naught F minus TF. Now what is T naught F here? Freezing point of solvent, pure solvent. Okay, and TF is freezing point of solution. Okay, so now KF is again freezing depression constant, M is molality. Okay, now coming to the next and the last colligative property, that is osmotic pressure. Now osmotic pressure formula is pi, it is denoted by pi, that is CRT. Here C is molarity. Remember, C is molarity. Okay, R is gas constant. Okay, R is gas constant and T is temperature in Kelvin. Okay, so now we can substitute this molarity as W2 into 1000 by M2 into volume of the solution in ml dot R dot T. Okay, so yes, these are the 4 colligative properties. Next we need to talk about abnormal molar mass. So when this abnormal molar mass comes, or when we need to talk about this, when the electrolytes either associate or dissociate. Okay, so when we have the electrolytes, whether they undergo association or dissociation, and we calculate the molar mass using colligative properties, we get wrong answer, right? So this wrong answer or these wrong calculated molar masses are called as abnormal masses. Now this can be corrected by multiplying a factor called as I, which is called as Van 't Hoff factor, right? So how to correct this one? Abnormal molar mass can be corrected using a factor called as Van 't Hoff factor, that is I. Okay, with I we can correct this one. Now what happens? For example, if I give you a solution of NaCl, it will dissociate to give you Na plus and Cl minus, so here I will be equal to 2. Now if I give you MgCl2, right, here Mg2 plus and 2 Cl minus I will get, so I is equal to 3. Now these I values are constant, or I can say these I values we can get easily like this if it undergoes 100% dissociation. If there is not 100% dissociation, then we need this formula. So for dissociation, this is the formula: alpha is equal to I minus 1 by n minus 1, where alpha is degree of dissociation. Alpha is degree of dissociation, I is your Van 't Hoff factor, n is number of particles, I is number of particles. Okay, now coming to for association, we will have again this one, alpha will be your degree of association, right, degree of association, and I is a Van 't Hoff factor, n is again the number of particles that gets associated. Okay, so now using this Van 't Hoff factor, what happens? The colligative properties get modified. So now what is your RLVP formula? We can write it here. I'll erase this part. Okay, so now if you see, we can just modify these chemical or this colligative properties. The first one, that is relative lowering of vapor pressure. Here I can write delta P by P naught is equal to I into XP. Okay, just a factor of I is added. Now if I see that elevation in boiling point, next one, elevation, one second, elevation in boiling point, delta TB, I can write I into KB into M. Then if I write freezing point, depression in freezing point, delta TF is I into KF into M. Now if I want to write for osmotic pressure, that is pi, pi is equal to I into C into R into T. Okay, so these are the formulas that we can use for colligative properties when the electrolyte, when your solute is either associating or dissociating. Okay, Fine. So yes, with this we have completed kinetics revision. I hope you have noted all the formulas. Let us quickly now go for the next chapter, that is electrochemistry. So in electrochemistry we have the chapter divided into these factors. First we'll talk about galvanic cell, then Nernst equation, then electrolytic cell, then products of electrolysis, conductance of electrolytes, and then lastly we'll talk about batteries. Okay. Now if you see here for galvanic cell, what all topics we have? For galvanic cell, first we'll discuss some important points regarding galvanic cell. Okay. Next we have cell notation, which is very important. Next we have cell EMF. Okay. Now coming to the next topic, that is electrolytic cell. Here we'll be talking about Faraday's first law and Faraday's second law. And then coming to conductance of electrolyte, which is a very important topic. Here we have so many subtopics. First I will be discussing some important terms, then I will be telling you important formulas, then variation of molar conductivities, then we will talk about Kohlrausch law. Okay. So yes, with this we will start our first topic, that is galvanic cell. Some important points regarding galvanic cell. So first of all, a galvanic cell will convert chemical energy to electrical energy. Okay. Chemical energy gets converted to electrical energy in galvanic cell. Now it is a spontaneous cell, so because it is a spontaneous process, delta G is negative here. Example is a Daniell cell, or you can write remote batteries. Okay, remote batteries, then your phone batteries. Okay, phone batteries. These all are examples of galvanic cell where some chemical reaction takes place to give you electrical energy. Now in these type of cells, what type of chemical energy is produced? Chemical energy is produced due to redox reaction. Okay. So some redox reaction happens in these batteries, due to which some chemical energy is produced. Now this chemical energy is converted to electrical energy. Okay. So now let us see first how to write the cell notation. Okay. So this is an example of Daniell cell. So how to write the cell notation? So for cell notation, if you see, we need to start from, what is cell notation? Cell notation is a way of representing a cell. Okay, cell notation, then I'll write here first what is cell notation. That is a way of representing a cell. Okay. So now in a galvanic cell, as you know, we have two sides. One is your oxidation half cell and one is your reduction half cell. So I told you a trick to remember, that is your lone, right? So you have to remember that on left side what will be there? Oxidation. O stands for oxidation. Then on A we have anode. Okay, and N is negative. So what I am saying, that on the left hand side of this galvanic cell, oxidation takes place. Oxidation takes place on anode, and the charge of the anode is negative. Okay. Now here only I will explain the mechanism also very shortly, then we can go to the cell notation. So see here what happens. First of all, zinc is there, right? So zinc will undergo oxidation. Oxidation means what? It will lose electrons. So Zn will come out of this rod as Zn2 plus. Okay, and it will release electrons here. Right. Now these electrons will move through the external circuit and will come here. Okay. Now what is there in this solution? Solution of copper. So this is copper sulfate solution. So we have copper 2 plus and SO4 2 minus. So these copper 2 plus will accept these electrons. Okay, these copper 2 plus electrons will accept these electrons and will get reduced. Okay. So like for example, now if I want to write the reaction, so what is happening? Oxidation, that is at anode. At anode what is happening? Zinc is undergoing oxidation, so I can write Zn is giving you Zn2 plus 2 electrons, right? And then if I wanted to write about reduction, so reduction is happening at cathode, right? So which is undergoing reduction? Copper. So copper 2 plus 2 electron is giving you copper, right? So Zn2 plus 2 electron, copper 2 plus 2 electron gives you copper. Now the term, see, every time we will not do this much big diagram to represent a cell, we can write it in the form of something called as cell notation. Okay. So for that you need to start with the left hand side. The first thing what you can see is zinc rod, right? So first we will write zinc. What is the physical state of this rod? Solid. So in bracket I wrote solid. Then this zinc rod is in contact with zinc sulfate solution. So Zn2 plus, which is in the aqueous phase. So you can write Zn2 plus aqueous. So between this Zn and this Zn2 plus there is a what was there is a single line, okay, which differentiates the two phases. Then coming to, then you can see there is something called as this U-shaped tube, which is called as salt bridge, that is represented with two lines, okay. Now this salt bridge is in contact with Cu2 plus. So again Cu2 plus and its state is aqueous. Then this Cu2 plus is in contact with this copper rod, right. So Cu2 plus aqueous, then this line, and then copper solid. Getting? So this is how you can represent any cell, okay. Fine. So now coming to calculation of cell EMF, how we need to calculate the cell EMF. So there is, you can see there are two sides, right. Here we have one rod and this one, and then we have on the other side another system, right. So here oxidation is going on and here reduction is going on. So this is an electrode here and there is one electrode here. So now here between this electrode and this electrolyte some potential is generated, we call it as oxidation potential, and here the potential is generated, that is called reduction potential, okay. So now what happens, the potential difference between the two electrodes of a galvanic cell is called as cell potential and is measured in volts. So the difference between the potential here and the potential here is called as your cell potential. The cell potential is the difference between the electrode potentials of the cathode and anode. So how do we get the formula for here? E of the cell is equal to E of cathode minus E of anode, okay. So here I will mention that when I talk about electrode potential, I am talking in terms of reduction potential, okay. So the IUPAC has told that all the electrode potential should be represented in the form of reduction potential. So E naught of cathode minus E naught of anode, okay. So remember, left side is anode, okay, and right side is your cathode. So if I see Daniell cell, right, Daniell cell, here it was zinc and here it was copper. So if I write, so I will write E naught of the cell of Daniell cell will be equal to E naught of copper 2 plus 2 copper, that is cathode, and this is the reduction potential, minus E naught of anode, that is Zn 2 plus 2 Zn, okay. So cathode minus anode. Getting? Okay, now coming to next one, Nernst equation. What is the use of Nernst equation? Nernst equation is also used to calculate the cell EMF. Now a question may arise, ma'am, just now you told a formula to calculate the cell EMF, then what is the difference? So I'll tell you that this formula we can use only, you see this knot I have given, what does this knot represents? It represents the standard potential. So when this electrolytes that is present here, okay, if its concentration is 1 molar, electrolytes present here is 1 molar, then we can use this formula, okay. But if it is not 1 molar, then it comes under non-standard conditions, and in that case we use the Nernst equation, okay. So now Nernst equation we can calculate for electrodes also and for cell also, okay. So if you have dipped a particular electrode, like if you have dipped zinc with zinc sulfate, okay, and this is zinc rod, okay, and this is zinc sulfate, but the concentration of this zinc sulfate is not equal to 1 molar, then we can calculate the electrode potential generated here, okay. That is called as your Nernst equation for electrode, and if the cell is there, means it has both oxidation and reduction potential, then we can calculate the Nernst equation for the cell also, okay. Fine. Now let us do here. This I am giving you an example of, suppose one metal is there with n plus electrons, it is gaining n electrons to get converted to m solid, right. So now how to calculate the Nernst equation for this one? That is E of the electrode potential of this rod is equal to E naught value, means the standard value, minus RT by NF log of concentration of the product side minus the concentration of the reactant side, okay. So here what happens, for solids, remember, for solids the concentration is equal to 1, okay. For solids the concentration is equal to 1. So now I can write EMN, this one minus this one is RT by NF by this much. So because this one is 1, so I will get 1 by Mn plus. Now if I substitute these all values, R value is 8.314, T is 298 Kelvin, and 25 degree 298, and Faraday is 96500, then I will be getting this value as E of Mn plus 2 Mn, okay, is equal to E naught minus 0.059 by n log of, okay, 1 by Mn plus, Okay, so this is the formula that you have to remember, which we have to use in our calculations. Okay, so how I got this log? I multiplied 2.303. So 2.303 into R into T by F will give you 0.059. Okay, divided by N is there. Okay, so what I am saying here, see, 2.303 into R into T by F is equal to 0.059. Okay, now what is R here? R is 8.314, T is 298 and F is 96500. Okay, fine. Now coming to next one, Nernst equation for a cell. Cell means both the electrodes we are counting. So here I will tell you that you can write it in the same way. E of the cell is equal to E naught of the cell, means the E naught of the cell means the electrode potential you can calculate by cathode minus anode, the standard electrode potential, minus, here you can use 2.303 RT by F log of, now see, here this is a solid, so its concentration will be not taken. This is an ion, aqueous ion, so concentration of the ion on the product side divided by the concentration of the ion on the reactant side. It is always products by reactants. Okay, so now here you have to remember that if there is any stoichiometric coefficient, then that power should be taken. Okay, so now if I modify this equation, okay, I will get E of the cell is equal to E naught of the cell minus 0.059 by N log of Ni2 plus by Ag plus square. Getting? So many of the students forget to add this stoichiometric coefficients here. Okay, so do not forget, remember that the stoichiometric coefficient, if it is there, it should be taken in the log term. Okay, fine. Now coming to the next topic, that is electrolytic cell. So very easy this is, it converts just opposite to galvanic cell, electrical energy to chemical energy. Okay, so it is a non-spontaneous process. Delta G for this reaction is positive and anode is positive and cathode is negative. Okay, so this is what is different in galvanic cell. In galvanic cell, anode is negative and cathode is positive, but here anode is positive and cathode is negative. Okay, now coming to examples, it is used for obtaining pure metals. Okay, when you do electroplating, so I can write in electroplating. Okay, in electroplating, the concept of electrolytic cells are used. Now next we have Faraday's law. So what is this Faraday's law? Faraday's law, you can see there are two Faraday's law, Faraday's first law and Faraday's second law. Now first I will tell you, okay, first we will go to Faraday's first law. What does it say? That the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte. Okay, so now see, what does it say? Suppose I have a I am having a cell, electrolytic cell. In electrolytic cell, both the anode and cathode are present in the same container. Okay, now what happens? Here some electrolyte is there, A, B, suppose A plus and B minus is there. Now what happened? Cathode, anode is positively charged here and cathode is negatively charged here. So what will happen? This A plus will move towards the negative electrode, right? Because it is having plus charge, so it will get attracted towards the negative electrode. Now what will happen here? Once it goes there, at cathode always reduction takes place. So A plus will undergo reduction, right, by gaining one electron to form a solid. Okay, so now what happens here? This A will become solid and will get deposited here. Okay, so our questions will be to calculate this amount of A deposited. Okay, so for that we use the Faraday's law. The formula is M is equal to Z into I into T. Okay, so what is saying? The mass deposited here is directly proportional to the current that you are passing, or I can say M is proportional to I into T, because Q is equal to IT. To remove this proportionality constant, we multiply something called as Z. Now how to calculate Z? Z is molar mass. So suppose copper is getting deposited, so molar mass of copper divided by N, how many electrons are used in its deposition, into 96500. Okay, fine. Now coming to Faraday's second law. So Faraday's second law is used when you have two cells and both you are passing same amount of current to both. Now for example, you see we have one second. So okay, so I'll give you one example. A diagram here we'll draw and we'll understand. Suppose you have two cells. Okay, you have two cells here. Okay, this is one electrolytic cell, this is one electrolytic cell. Here you have AB and here you have CD. here A plus B minus, C plus D minus, okay, and this is, okay, these two are also connected somehow, and this one is getting deposited here, this one is getting deposited here. A plus is getting deposited here, C plus is getting deposited here. Now to both the cells we have applied same current, okay. Then what we can say that the mass of A depositor, mass of 1 deposited by mass of 2 deposited is equal to equivalent weight of 1 by equivalent weight of 2. So what is this E stands for? E stands for equivalent weight, okay. How to calculate equivalent weight? Molar mass divided by n factor, okay, that is your equivalent weight. Getting? Okay, now coming to next one, the fourth topic, that is products of electrolysis. So this is very, very important. Certain examples you must remember. I'll be telling you which one are important, okay. So when you take molten NaCl, okay, so what is there here? You have Na plus, okay, and you have Cl minus. So Na plus, cathode is negatively charged, anode is positively charged. So what will happen? Na plus will move towards cathode, at cathode there is always reduction, it will undergo reduction and form Na metal, right. Now Cl minus will go towards the anode, it will undergo oxidation and form chlorine gas, okay. These reactions no need to remember, okay. Now coming to aqueous NaCl. In aqueous NaCl what is there? There is Na plus, okay, there is Cl minus, there is H plus and there is OH minus, right. So now both Na plus and H plus wants to go towards the cathode, but H plus has higher reduction potential, so H plus will undergo reduction and form H2 gas. So you see the products are different here. Now chlorine and OH minus, again chlorine has more oxidation potential, so chlorine will undergo oxidation and give you Cl2 gas, okay. So these two examples are important, okay, this is important and this is also important examples. Now other things which is given in your NCERT also you should be knowing. Dilute H2SO4, okay. In that what we have H plus, okay, SO4 2 minus, okay, and from water also you have H plus and OH minus, right. So what will happen here? At cathode there is no issue that both are H plus, so hydrogen will go and will undergo reduction. But here out of SO4 and OH minus will undergo oxidation and will give you O2 gas, okay. Now coming to concentrated H2SO4, if you take there is H plus and SO4 2 minus, right. So H plus will undergo oxidation and H plus will undergo reduction and produce H2 gas, and SO4 2 minus will undergo oxidation and will give you S2O8, okay. So these are the products when you take aqueous and molten, the different products are formed, okay. Now coming to next one, very, very important topic, high weightage topic, that is your conductance of, so here there is small, okay, conductance of electrolytic solutions actually, okay. So I'll change this is conductance of electrolytic solutions, not cells, conductance of electrolytic solutions. Now what do you mean by electrolytic solutions? So those solutions which can carry electricity are called as electrolytes. So how these electrolytes can conduct electricity, that is what we are going to study in this particular section, okay. So the conductance of electricity by ions present in the solutions is called as electrolytic or ionic conductance. So you have seen metallic conductors, right? Metals are also good conductors of electricity and they conduct by the use of electrons present in the rod, right. But here what these electrolytes do, they conduct due to the presence of ions in them, okay. So that is why we call it either ionic conductance or electrolytic conductance, okay. So here some very, very important terms and definitions that you need to know with the symbol so that you do not confuse. So when I was studying this chapter in my school, I used to get a lot of confusion with these words. You can see conductance, conductivity, resistance, resistivity, cell constant, right. So these type of new terminologies are very, very confusing. So that is why I have given you a table, okay. So you need to know the term, you need to know the symbol and you need to know the SI unit of that, okay. So yes, now let us see here. The first term that I told you is resistance, right. So resistance symbol is R. What do you mean by resistance? Something that opposes the flow of current, okay, and its unit is ohm. It can be represented in this way or OHM. Next coming to resistivity, resistivity is denoted by a symbol rho, Okay, this symbol is called as rho. Now resistivity of a substance is its resistance when it is 1 meter long and its area of cross section is 1 meter square. So when a substance is 1 meter long and its cross sectional area is 1 meter square, at that time whatever resistance it faces, that is called as resistivity. And here the units of resistivity is either ohm meter or ohm centimeter. Now coming to conductance, conductance you should remember is opposite of resistance. Okay, G symbol is there, so I can write it as opposite to this one. So 1 by ohm, so I can write like 1 by R. So 1 by R means 1 by ohm, so ohm inverse will come. Now ohm inverse is told as Siemens or S. Okay, the next term here is conductivity. Okay, conductivity is kappa value and it is the conduction by electrolyte per unit volume. Okay, so in 1 unit of volume, okay, suppose you have a container here, you see, suppose you have a container. Okay, this container capacity is 5 liter. So in this per unit, in 1 liter volume of electrolyte, okay, 1 unit volume of electrolyte, how much electricity is conducted by per unit volume of electrolyte is called as conductivity, and it is denoted by the letter kappa. Okay, we to tell it as kappa, K. Okay, and its unit is ohm inverse, meter inverse, or you can write in place of ohm inverse as S meter inverse, ohm inverse centimeter inverse, or S centimeter inverse. Okay, now coming to cell constant is represented G star and we write it as L by A, that is length by area. So its units are meter inverse or centimeter inverse. Now coming to the next one, that is molar conductance. Molar conductance is denoted by lambda m. So it is the conductance of all the ions produced by 1 mole of an electrolyte in a specific volume of solution. So you need to take 1 molar electrolyte and you have to see how much electricity is conducted by this particular 1 molar electrolyte. Whatever value we get, that is called as lambda m or molar conductance. Its unit is S meter square mole inverse or S centimeter square mole inverse. Okay, fine. Now coming to formulas here, these are very important formulas. Resistance R is equal to rho into L by A. Resistivity is just, you can see from here, so it will become rho is equal to 1 R into A by L. Okay, now cell constant is your this term G star, that is L by A. Now conductance is opposite of resistance, I told you, so G, so opposite of this one is 1 by R, or you can write it in this term. So we can write it as like this also, G is equal to, okay, opposite of this one, A rho by L, A into rho by L. Next, conductivity, that is resistivity, so it is opposite of conductivity is opposite of resistivity, so you can write 1 by rho, right? Now 1 by rho you can write it as 1 by R into L by A. So here you can see I can write 1 by R is nothing but conductance G, right, and L by A is cell constant G star. So we can write it as in this way. Molar conductivity formula, lambda m is kappa into 1000 by C. Here kappa is conductivity and C is concentration. Okay, fine. These all formulas are very important for revision. Okay, next coming to variation of kappa and molar conductivity with concentration. So I'll tell you, for conductivity what happens, see, when what I say with concentration, right? So conductivity is the I can say conduction or conduction of electrolyte per unit volume. Okay, so what happens when you dilute, or I can say that means when concentration decreases, okay, concentration decreases, kappa will also decrease. Okay, that is what you have to remember, kappa decreases when concentration decreases. Okay, now coming to molar conductivity. So in molar conductivity what happens, if you see the formula, lambda m is equal to kappa into 1000 by C, right? So if concentration decreases, molar conductivity will increase. Okay, when I'm saying concentration decreases, I mean I'm diluting the solution. So with dilution what will happen, molar conductivity will increase. Okay, now the molar conductivity increase is different for weak electrolytes and for strong electrolytes. For weak electrolytes the increase is more, for strong electrolytes the increases there, but relatively less as compared to weak electrolytes. Okay, so what is the reason for that? For weak electrolytes the increase is more because dissociation increases. You can see because increase in the dissociation of ions, more number of ions are produced. In strong electrolytes also molar conductivity increases, but the reason here is due to the increase in the mobility of ions, right? So mobility of ions increases, that is why the conductivity increases in case of strong electrolytes. Here number of ions increases, and that is why the conductivity increases for weak electrolytes. So the increase is more in this case, increase is less in this case. Okay, weak electrolytes, strong electrolytes, molar conductivity increases, but for weak electrolytes it increases more, but for strong electrolytes it increases less. Okay, now here something is there from where 2 years these questions have been asked here. So this strong electrolytes, we can, like, the molar conductivity can be given with a equation lambda m is equal to lambda naught m minus A into root over of C. Okay, now what is this lambda naught m, we'll discuss after some time. This A is a constant. Okay, now A is same for same type of electrolytes. What do you mean by same type of electrolytes? Suppose I tell you NaCl, okay, and KBr. See, this is plus 1, this is minus 1, this is plus 1, this is minus 1. So this is plus 1, this is minus 1, I'll call it as 1, 1 electrolyte. This is also called as 1, 1 electrolyte. Now if I give you an example, right, MgCl2, okay, and CaCl2. So Mg is plus 2, chlorine is minus 1, this is plus 2, this is minus 1. So these are your 2, 1 type. So now you have to remember that for same type of electrolyte, like for NaCl and KBr, the A value will be same. Okay, for MgCl2 and CaCl2, the A value will be same. For KCl and MgCl2, they are two different types of electrolyte, their A values will be different. Okay, so now if you see, if I want to draw this graph for here, so if you see, first see the if you have to see from this side, the concentration is decreasing, right? So 1 second, yeah. So now if you see from 0.4 to 0.4, the concentration is decreasing in this side. If the concentration is decreasing for the weak electrolyte, you see how drastically you can see the change in the molar conductivity, right? So if you see at 0.4, the molar conductivity was something here, but when the concentration is decreasing, it has almost reached up to 400, right? So there is a drastic increase in the conductivity of weak electrolytes. The reason for this is the number or the dissociation of ion increases. Now if you see strong electrolyte, in strong electrolyte it was before here and now it is here. There is not much difference, but in weak electrolytes we have a very drastic change. Okay, so that is there, very important thing. Now what is limiting molar conductivity? So I told you something, I'll explain later. So that is your limiting molar conductivity. See, when the concentration approaches to 0, we can see in this graph once again. See, when the concentration approaches 0, what is the conductivity at that time? Okay, very dilute solution, the conductivity at that time is called as limiting molar conductivity. Okay, and this limiting molar conductivity is denoted by lambda naught m. Okay, now what happens? Now if you see, what is this Kohlrausch law? So limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. So if I want to say like NaCl, okay, what is the limiting molar conductivity of NaCl? So I can write it as limiting molar conductivity of Na plus limiting molar conductivity of Cl minus. Okay, now suppose you want to write limiting molar conductivity of MgCl2. So that will be equal to limiting molar conductivity of Mg2 plus 2 times of limiting molar conductivity of Cl minus. Okay, like this we can write the equations. Okay, fine. Now coming to what is the use of this Kohlrausch law? So Kohlrausch law you can use to calculate the degree, that is the degree of dissociation alpha. Alpha value is lambda m by lambda naught m. So what is lambda m? This is the molar conductivity. Okay, this is molar conductivity. And what is lambda naught m? This is limiting molar conductivity. Limiting molar conductivity. Okay, getting? Now if you see, we can write that acid dissociation constant Ka is equal to C alpha square by 1 minus alpha, and in place of alpha you can substitute this data and will get this value. Okay, and then another important utilization of this Kohlrausch law is it is used to calculate the lambda limiting molar conductivity for weak electrolytes. Okay, fine. Now let us go to the next topic, that is batteries. So for batteries, you should remember we have two types of batteries, primary batteries and secondary batteries. Primary batteries are those which can be used only once, cannot be recharged, so reaction occurs only once, cannot be reused again. And in this one, secondary batteries, they can be recharged if by passing the current in opposite direction, and it can be used again. Okay, it can be reused. Okay, now coming to examples of primary batteries, we have dry cell and mercury cell. These are the examples of your primary batteries. And in secondary batteries, we have lead storage batteries and nickel cadmium batteries. Okay, now what you can see these reactions for anode and cathode. So just I'll tell you, you need not remember the reactions, just remember this anode and cathode is made up of what. For dry cell, anode is zinc and cathode is MnO2. For mercury cell, anode is zinc and cathode is HgO, mercury oxide. Okay, now if you see in cell, the next one, secondary cells, in lead storage, this is very important, lead is your anode and lead oxide is cathode, and in nickel cadmium cell, cadmium is anode and nickel oxide is cathode. Okay, now here this is the complete reaction. You can add these two anode cathode reactions to get this reaction. Similarly, lead reactions, you can add these two reactions to get this one. Okay, now here one important thing that I'll tell you, that see this reaction that we have got, right, this reaction is for discharging of battery when the battery is used. Now when charging, when you recharge the battery, the reactions will change, right, the reactions will be opposite. Now this reaction will become opposite, this reaction will become opposite. So that means what happens, at anode what reaction will take place, PbSO4 will get converted to Pb. Okay, and at cathode what reaction will take place, PbSO4 will get converted to PbO2. So you can see now on charging the battery, the reaction is reversed and PbSO4 on anode and cathode is converted to Pb and PbO2 respectively. Okay, so this one will happen at anode and this opposite reaction will take place at cathode. Okay, so now coming to, so with this we have revised electrochemistry, all formulas, all concepts, all topics we have covered. Now we'll go to the last chapter of physical chemistry for PU2, which is a very high weightage topic, that is chemical kinetics. So in chemical kinetics we have rate of reaction, factors affecting rate of reaction, then we have effect of concentration, which is very high weightage topic, then we have effect of temperature, effect of catalyst, and then we have collision theory. Okay, here in rate we will be discussing two types of rate, one is average rate, one is instantaneous rate, then we will be talking about differential rate equation. Now in effect of concentration we will talk about rate law and rate constant, then we will talk about order and molecularity, integrated rate equations, half-life, and then pseudo first order reaction. Okay, so yes, now let's get started. First is rate of a reaction. So there are two types of rate of a reaction, one is average rate, another is instantaneous rate. So in average rate, measured for a certain time interval, it is represented by a triangle, that is delta, and instantaneous rate is measured for a particular instant and it is represented by d by dt. Okay, now here you can see that this graph where the concentration is decreasing, that is for reactants, and this graph is for products, because here the concentration is forming, right. So I can write that this graph is for reactants. Okay, because with time what will happen, react concentration will decrease, and this graph is for products. Okay, now if you want to see average rate, you can measure for a particular time interval. So you can see for T1 to T2, if you measure in this particular time interval, we can calculate the average rate. Next, if you want to calculate instantaneous rate at a particular instant, you can calculate. Similarly, you can do it for product graph. So if you see here at particular T1 and T2, here and here, okay, I'll mark it. Okay, so this is R1. So at this particular instant, if you want to calculate the average rate, we'll get dP by dt, and if you want to calculate at a particular instant, we have to draw a slope and we can calculate, so that is instantaneous rate. Okay, fine. Now coming to the differential equation. So how to write the differential equation? So the differential equation you can write like this. See, rate is equal to, okay, minus the stoichiometric coefficients, minus of 1 by 2 d of N2O5 by dt. Okay, so now here remember that for reactants we have to use the sign negative. Okay, that will be equal to 1 by 4 positive, because this is product, right, dNO2 by dt, and that is equal to d of O2 by dt. Okay, now coming to here, if I write rate is equal to d of N2 by dt, so minus I'll use, is equal to minus of 1 by 3 dH2 by dt equal to plus 1 by 2 dNH3 by dt. Okay, so like this we can write the differential rate equation for both. So you have to remember, products will be positive, reactants will be negative, and the stoichiometric coefficient should be written in denominator. Okay, fine. Now factors affecting rate of a reaction, we have the first factor concentration, then we have temperature, and then we have catalyst. So what happens, if we increase the concentration, rate will increase. If we increase the temperature, rate will increase. If you use a catalyst, then the rate will increase. Okay, so now coming to the first factor, that is concentration. Here we have a lot of things to cover. So first is your rate law and rate constant, then we'll study about order and molecularity, integrated rate equation, half-life, and then pseudo first order reaction. Okay, so now let us quickly see what is a rate law. I'll tell you, rate law is an expression which gives you the expression in which the reaction rate is given in terms of the molar concentration of the reactants, with each term raised to some power which may or may not be equal to the stoichiometric coefficients. Now for example, if this is a reaction, okay, so its rate will be proportional to the concentration of the reactants raised to some power x and y. Okay, so this x and y may or may not be equal to A. Okay, it may be equal, and y, it is not compulsory, it may or may not be equal to y. Now to remove this proportionality, we will multiply one constant, and that constant k is called as your rate constant, right? So what is k here? K is rate constant. Okay, now the unit of rate constant is moles to the power of 1 minus n, liter to the power of n minus 1, and second inverse. So what is this n here? N is order, about which we will discuss just now. Okay, so order we are going to cover. So you have to remember, unit of rate constant is mole 1 minus n, liter n minus 1, and second inverse. Okay, now coming to order and molecularity. So order definition I'll tell you later. First let us understand that I told you when concentration will change, the rate will change, right? So the order generally like tells you how the rate will change, how the rate changes when concentration changes. Okay, how the rate will change when the concentration changes. Okay, that means if suppose you are doubling the rate, if you are doubling the concentration, then whether the rate will also get doubled, or rate will become 4 times, or there is no change in the rate. These all things is told by order of a reaction. Okay, so now for example, okay, first let us see what is the exact definition of order. So if this is the rate law, the x, we can say x is the order with respect to A. Okay, y is the order with respect to B. Then the overall reaction, okay, for this overall reaction, if I want to calculate the order, overall is x plus y. Okay, order of the reaction is x plus y. Now suppose I'll say that R is equal to k into some 0th order, or I'll say first order. Okay, let us make it first order. Okay, that means what? If you suppose I am doubling the concentration, rate will also become double. So I'll write 2R is equal to k into 2 times of A, right? So that is 2Ka, or I can say 2R. So that means when you double the concentration, rate is also becoming double. That means it is a first order reaction. If it is a second order reaction, for example, okay, if you are doubling the concentration, it will become 4 times, right? So what I can say that when I am doubling the concentration, rate becomes 4 times, then it is a second order reaction. So like this, order will tell us how if you change the concentration, the rate will change. Okay, Fine. So okay, now coming to molecularity. So molecularity is nothing but the number of species reacting in an elementary step. Okay, so for example, if you see this first reaction, only one reactant is there, so molecularity is 1. Here 2 reactants are there, so molecularity is 2. Here 2 NO and 1 O2, 3, so this is molecularity is 3. Okay. Okay, now coming to integrated rate law equation. So integrated rate equation is used when you have to use time as a function. Okay, when we want to also calculate, we want to also get information regarding time. Okay, then we need to use integrated rate equation. Okay, now integrated rate equation we are going to study for 0th order and for first order. Okay. Okay, now what is the use of this integrated rate equation? It is used to calculate, suppose you have started, calculate how long it takes for a reaction to progress. Suppose you have started with some amount of reactant A, and you want to know that, suppose you started with 1 mole of A, okay, and you want to know that after how much time it will become 0.8 moles. So then we can use this integrated rate equation. You can also calculate determine the amount of product or reactant present. Suppose you started with 1 mole of A, you have done the reaction for 10 minutes, now how much A is left behind or how much B is produced, that we can calculate using this reaction, this integrated rate equation. It is also used to determine the order of a reaction. Okay, so fine, now let us see 0th order. So see, 0 order reaction means what? The rate of the reaction is independent of the concentration. 0th order means the rate of the reaction is independent of the concentration. So how we can say, see, for any rate, rate is equal to K into A to the power of N. 0th order means N is equal to 0, so I can say that rate is equal to K, right? So that means rate does not depend on the concentration, so whatever changes you make in the concentration, for a 0 order reaction, the rate will remain constant. Okay, so now if you see integrated rate law, so here KT is equal to A naught minus A. Okay, so here K is your rate constant, T is time. Okay, A naught is the initial concentration and A is the final concentration. Okay, now coming to unit of K. So unit of K, as I told you, what was the formula for, general formula for K? Mole 1 minus n, liter n minus 1, second inverse. So if I substitute n is equal to 0, so I'll get mole liter second inverse, right? So that is what we'll get as the units of K. Now coming to the graph here, if I plot this graph for here, I'll get a straight line with a negative slope. Okay, now coming to the examples of 0th order, this is very, very important. The decomposition of gaseous ammonia on a hot platinum surface and thermal decomposition of HI on gold surface. Okay, so generally when some catalyst is used and some decomposition happens on some particular surface, these reactions follow 0 order reactions. Okay. Now coming to first order reaction, so the rate of the reaction is proportional to the first power of the concentration. So if I write again rate law, so you can see here, so rate law R is equal to K into A. So if I double the concentration, rate will become double. If I triple the concentration, rate will triple. Now integrated rate law, here is KT is equal to 2.303 log A naught by A. Again these terms are very familiar. K is rate constant, T is time. So I will write here otherwise, K is rate constant. Okay, next T is time. Okay, then we have A naught. A naught is initial concentration and A is final concentration. Okay, of the reactant. Now unit of K, if you see, what was the general formula for K? It is mole 1 minus n, liter n minus 1, second inverse. So if I substitute n is equal to 1, this will become 0, this will become 0, only unit left is S inverse. Okay, fine. Now coming to examples. Okay, graph of first order. So these are the graphs you can draw for first order. And next coming to examples of first order, this is very, very important. All radioactive decays are first order. Decomposition of N2O5 and N2O is first order. Hydrogenation of ethene is also first order. Okay, so these examples you must remember. Okay, okay. Now coming to half-life. So what is half-life? Half-life is of a reaction is the time in which the concentration of a reactant is reduced to half of its initial concentration. It is denoted by T half. Like suppose you have started with 2 moles of A. So by how much time that 2 moles of A gets converted to 1 mole of A? Half, it will become half of its initial concentration. That time is called as half-life. Okay. So now if you see so T half is proportional to 1 by A to the power of n minus 1. Okay. And A is what? In concentration. Now if you see for half-life, we have two formula for 0th order and for first order. For 0th order, the half-life formula is A0 by 2K, and for first order it is 0.693 by K. Now what do you observe here? That the half-life T half for first order is independent of initial concentration. That means what? See, suppose you started with 2 moles of A, it will become half in 1 mole. Suppose this time takes X, then from 1 to 0.5 also it will take X, 0.5 half, that is 0.25, this is also X, 0.25 to 0.125, this is also X. So that is what half-life of a first order. You can easily guess that whatever is the initial concentration, it is not affected with that. Every time when the concentration becomes half, the half-life still remains the constant. Okay. Now for first order, I will be telling you one more formula, that is T half T 99.9% is equal to 10 times of T 50%. Okay. So this formula also you have to remember. Many a times you can easily solve this question using this formula. Okay. So that means the time required for completion of 99.9% of a reaction is equal to 10 times of T of 50%. Okay. Fine. Now coming to a pseudo first order reaction. What is a pseudo first order reaction? So a pseudo first order reaction is a reaction that appears to be first order, but actually it is a second order reaction. Right? When we can have pseudo first order? It happens when one or more reactants are present in much larger concentration. Now suppose see, there is a reactant, suppose A plus B is giving you C. Now if I want to write the rate law, I will write R is equal to K into A into B. Now what happens if B is present in excess? So what happens, whatever changes you make, whether you decrease the concentration or you increase the concentration of B, it will not be affected, because rate will not be affected, because B is present in infinite amount. So in that case, this B is like irrelevant, and I can write it as Ka. So actually it is second order, but it appears to be first order because one of the reactant is present in excess. Okay. Now examples of these are hydrolysis of ethyl acetate and inversion of cane sugar. Okay, these two examples you must remember. Now coming to the second factor, that is effect of temperature. So here you have to remember that for every 10-degree rise, the rate constant is nearly doubled. Okay, if you increase the temperature by 10 degree, like from 17 to 27 if you make, the rate constant will almost be equal to double. Okay. Next, Arrhenius equation. So how the temperature affects the rate? Okay, the temperature dependence of a rate of a chemical reaction is given by Arrhenius equation. So now if I say the dependency of concentration on rate, concentration on rate is given by rate law. Similarly, the dependency of temperature on rate, that is given by Arrhenius equation, and the formula of Arrhenius equation is equal to K into A into e to the power of minus Ea by RT. Now let us discuss the terms here. K, as you all know, is your rate constant. Okay. Then A is called as Arrhenius factor or Arrhenius constant. Arrhenius constant. Next we have Ea. Ea is activation energy. Okay. Ea is activation energy. Then R is gas constant, okay, and T is temperature. Okay, clear? So now what is this activation energy and all we'll discuss. So now you see here. Now what happens? This is H. Suppose in this reaction you can see H2 and I2, right? Are the reactants H2 and I2 are reacting to give you HI, but a reactants cannot directly give you product. Okay, they will be converted to something called as activated complex. So the energy required for the reactants to get converted to the activated complex, this is called as your activation energy. Okay, so that is activation energy. Getting after this much energy is provided, they will get converted to activation energy. After that, they will form the products. Okay, fine. Now coming to next one, Arrhenius equation. If I tell it in terms of ln, I'll get this equation. Now we can draw a graph for this one. This is a straight line equation. So you can see y is equal to mx. Okay, so this is the slope, x is 1 by t here. Okay, and slope is minus Ea by r, negative slope. So minus Ea by r, this is x axis, so this is y axis and this is x axis. Okay, now what we can see, if we have two different temperatures, okay, if we have two different temperatures and you want to calculate the this one rate constant for two different temperatures, then the modified formula becomes like this: log of K2 by K1 is equal to Ea by 2.303 r 1 by T1 minus 1 by T2. So what is here? T1 is the first temperature. So K1 is the rate constant at T1, T2 is the second one. So I can say K2 is the rate constant at T2. Ea is activation energy, okay, R is gas constant, and yes, those are the terms that you have to know. Okay, now coming to Boltzmann distribution curve. So here what is it saying? Boltzmann distribution curve says that when you increase the temperature, the number of particles having energy, so this is at a normal temperature. Okay, now when you increases the temperature by 10 degree, okay, now see, this is at T, the first one, and the second one is at T plus 10. Okay, so now what it is saying, that see these number of particles, okay, which is present here after activation energy, after whatever particles are there, these are the particles which can form products. Okay, these are the particles which can form products. Now what happens here? When you, so earlier when the temperature was T, these many particles were there which can form products because their energy is greater than activation energy. Now when you increase the temperature by 10 degree, okay, the number of particles falling in this range has increased. Now these many more particles are there, so more particles can form product, and that is why the rate of reaction will increase. Okay, so if somebody asks you why when temperature increases the rate of reaction increases, the very simple answer is when the temperature increases, the number of particles having energy greater than activation energy increases, and that is why more number of reactants can form products, and that is why the rate of the reaction increases. Okay, fine. Now coming to talk about effect of catalyst. So what is a catalyst? A catalyst is something which increases the rate of the reaction without undergoing any change in itself. Okay, now how does the catalyst increases the rate? By giving an alternative pathway for the reaction. Okay, now if you are using a catalyst, what will happen? There will be no change in the Gibbs free energy and in the equilibrium constant. Okay, now you can see a graph here. So what exactly a catalyst do? The first reaction, if you see, this first reaction is without a catalyst, so this activation energy is here. Now when you use a catalyst, the rate of the reaction, the catalyst, if activation energy decreases. Now your question may arise, ma'am, what happens if activation energy decreases? How if activation energy is decreasing, the rate is increasing? So the answer to this lies in your Arrhenius equation. So if you see the Arrhenius equation, can we write like this? K is equal to A into 1 by e to the power of Ea by RT, right? So when I use catalyst, what will happen? Activation energy will decrease, right? If activation energy is decreasing, this whole fraction will decrease. E to the power of something will decrease, so I can say this whole denominator is decreasing. If this one is decreasing, then K will increase, right? So that is why we can say that if we use a catalyst, activation energy will decrease, as a result of which rate constant will increase. Okay, fine. Next, coming to collision theory. So collision theory tells us that it is a theory about how products are formed. Okay, so the first postulate here tells that the reactants are assumed to be hard spheres. Okay, and when these reactants collide, then we get products. Okay, now the number of collisions that takes place per second per unit volume is called as collision frequency and is denoted by Z. Okay, so now another factor which affects the rate of a chemical reaction is activation energy. So they says that the reactants should collide, that is fine, but they should collide with a certain amount of energy. Okay, the collision should have sufficient amount of energy. So based on that, they gave a formula, that is rate is equal to ZAB into e to the power of EA by RT. What is this ZAB? So there are two reactants A and B, okay, hard spheres, and ZAB is their collision frequency. Collision frequency. Okay. Now rate is equal to ZAB into e to the power of EA by RT. Getting? Now with this what happened? Now see. So they said that okay, that collisions will give you rate of a reaction, collisions will give you products, but the collision should be effective. Now what do you mean by effective collision? So this definition of effective collision has two parameters. One is they should have sufficient kinetic energy, and the collision should happen in proper orientation, means in proper direction the two molecules should collide. Then only we can get products, and these type of collisions where there is proper energy and proper orientation are called as effective collisions. Okay. So now if you see, okay, to account for the effective collisions, another factor P called as probability or steric factor is introduced. So now you can see one example. If you have read this SN1, SN2 reactions in organic chemistry, you might get it here. That suppose this is a reactant where this bromine has to go and OH minus has to attack. So this reaction can happen only if OH minus attacks from the back side. If OH minus is attacking from the front side, then the reaction will not happen. So in that case I can say that there has to be a proper orientation between these two, right? So that is why we can say when OH minus is attacking from the front side, you can see from this side, no products are formed, right? In this case no products are formed. But when OH comes from the back side, there is a formation of product. So there is also an importance of orientation factor, not only energy but also the orientation of the molecules is important. So to account for this orientation factor, we have another term, that is P, which will tell about the orientation factor, right? ZAB is telling about your collision frequency, and this factor will tell you about the energy, that is activation energy. Okay. So yes, so with this we have completed a revision of all the three chapters. I haven't gone to each and every detail, but I have explained all the major concepts. So if you want to study these chapters in detail, then please go and watch the solutions, 3 videos we have made on solutions, and electrochemistry also has 3 parts and kinetics has 2 parts. Okay, so those all video playlist will be there in our description section. So please go there, read once again if you are not understanding, because revision means we are not going each and everything, we are just recalling what are the important topics. Okay, so let us practice some questions. So the first question here is 5.5 milligram of nitrogen gas dissolves in 180 gram of water at 273 Kelvin and 1 atm pressure. Okay, so I can say that when pressure is 1 atm, number of moles nitrogen that has dissolved is 5.5 milligram. Okay, not moles, mass. Okay, in how much water? Mass of water is given to you as 180. Okay, next, due to nitrogen gas. So this 1 atm pressure is due to nitrogen gas, so I can write PN2, partial pressure of nitrogen. Now the mole fraction of nitrogen in 180 gram of water at 5 atm nitrogen pressure. So if pressure of nitrogen is 5 atm, okay, and the number of mass of N2 is we have to calculate. So they are asking how many mole fractions of nitrogen will be dissolved, right? Mole fraction of nitrogen if the number of moles of water is, or the mass of water is 180 gram. Okay, so here we have 2 questions, like you can see, pressure of 1 atm is equal to KH into mole fraction of nitrogen. Then at pressure 5 atm, okay, KH into mole fraction of nitrogen. So we need to calculate this value, mole fraction of nitrogen at what pressure? At 5 atm pressure. So KH is constant, so I can just take ratio of this one. So let us first calculate number of moles of nitrogen, that is given mass by molar mass. So 5.5 into 10 to the power of minus 3 by 28. Number of moles of water is again given mass by molar mass, so 180 by 18, that is 10. So how can I calculate now mole fraction of this one, N2? Sorry, mole fraction of N2 will be 5.5 into 10 to the power of minus 3 by 28 whole divided by 5.5 into 10 to the power of minus 3. So we can ignore this part, right? I told you in dilute solutions we can ignore the moles of solute, so I can just write here 10. Okay, so now if I want to substitute these values, I can write 1 by 5, okay, is equal to, so what I'll get, P1 atm by P5 atm is equal to mole fraction of N2 by mole fraction of N2 dash. I just write it as N2 dash. Okay, so I can substitute this one like this, 5.5 into 10 to the power of minus 3 by 28 into 10 divided by mole fraction of N2. Okay, so now if we solve this, okay, if you solve this, you will be getting around 10 to the power of minus 4. The correct answer for this question will be option number D. So now let us see the next question here. Solute X dimerizes in water to an extent of 80%. Okay, 2.5 gram of X in 100 gram of water increases the boiling point by 0.3 degree Celsius. The molar mass of X is. Okay, so now if we have this formula, delta TB is equal to I into Kb into M. So here do you remember the Kb value I forgot to mention, that is 0.52. Okay, so now if I want, first of all I need I value. It is a case of association. So association formula is alpha I minus 1 by 1 minus n by 1. So that is 0.8. I want to calculate. This is dimerizes, so 1 by 2 minus 1. So I value will be 0.6. So I can substitute delta TB is 0.3. I value is 0.6. Kb value is 0.52. Okay, molality, given mass of the solute, that is 2.5. Okay, by molar mass into 1000, right, by 100. Mass of the solvent is 100. So if I solve this, I'll be getting M as 26. Okay, correct answer for this question will be option number C. Okay, now coming to question from your equilibrium constant here. So H2 and 2 AgCl gives 2 Ag plus delta G value, del E naught value is given, that is 0.22. The equilibrium constant you need to calculate. So if you have this formula, E naught of the cell is equal to 0.059. Okay, so one second. Okay, E naught of the cell is equal to 0.059 by n log of K. Right, so E naught of the cell is how much? I can say it is 2.22. Right, this one for easy calculation, let us make it 0.6. Okay, and n value if you see here, H2 to H plus 2 Ag, so number of electrons is 2 into log of K. So if you see, you will get 0.03, so 22 by 3, 7 point something I'll get is equal to log K, right, 7 point x suppose I write, then K will be equal to 10 to the power of 7 point x, so I can write 10 to the power of 7 into 10 to the power of x. So this 10 to the power of 7 has to come, so the correct answer for this question will be option number A. Okay, next doing with this question, by passing electric current, NaClO3 is converted to NaClO4 according to the following equation. Okay, how many moles of NaClO4 will be formed when 3 Faradays of charge is passed through NaClO3? Now if you see NaClO3 to NaClO4, what is the charge of chlorine here? If you see, sodium is plus 1, this is x minus 6, so I can get x is equal to plus 5, right? And here if you see, it is 1 plus x minus 8 is equal to 0, x is equal to plus 7, right? So I can say that to convert 1 mole of NaClO3 to 1 mole of NaClO4, I need 2 Faradays. So with 2 Faradays of electricity, we can get 1 mole of NaClO4, right? Now with 3 Faraday how much I'll get? Then with 1 Faraday how much I'll get? 1 by 2 moles. With 3 Faraday I'll get 3 by 2 moles, that is 3 by 2 moles means 1.5. The correct answer for this question will be option number C. Okay, now let us do some questions from kinetics also. For a reaction, A plus 2B gives products when concentration of B alone is increased, half-life remains the same, right? So if you are changing the concentration, the half-life is remaining the same. That means half-life is independent of the concentration. Now this means what? This is a first order reaction with respect to B. When concentration of B alone is increased, the half-life remains the same. So I can say with respect to B, it is first order. Okay. Next, if concentration of A alone is doubled, the rate remains the same. Means what? The rate does not depends on the concentration of A. So that means I can say with respect to A, it is 0 order, right? Now the unit of rate constant for the reaction. So I can get that R is equal to K into, okay, with respect to A it is 0th order and with respect to B it is first order, because the half-life is independent of concentration. So I can write R is equal to K into B. Okay, so now it is a first order reaction. So the first order reaction, the unit of rate constant is second inverse, right? Correct answer is option number A. Now coming to next question here, the activation energy of a chemical reaction can be determined by. So for activation energy, how can we determine? From Arrhenius equation, evaluating the rate constant at two different temperatures. So we have this formula, log of K2 by K1 is equal to EA by 2.303 R 1 by T1 minus 1 by T2. So if we have the equilibrium rate constant at two different temperatures, then we can calculate the activation energy. Okay, so the correct answer for this question is option number A. Okay. Okay, now I want to mention two formulas that I have missed in this revision. So please remember two formulas from electrochemistry at equilibrium. So okay, E of the cell, E naught of the cell is equal to 0.059 by N log K. Please add this formula. Another formula is delta G is equal to minus NF E naught of the cell. Okay, so please I request you to add these two formulas also in the electrochemistry part. Okay, these two are also important formulas which I missed. Okay. So yes, this was the entire revision of the complete physical chemistry, including 3 chapters of PU2. I hope you would have revised everything, you would have done all these formulas, written all these formulas, and have also practiced some more questions. Okay, so yes, please stay with me so that we can master each and every topic in chemistry and we can hit that perfect 60 score in a KCET 2025 examination together. Okay, so yes, every day you need to watch the classes at 6 p.m, make notes, do practice questions. If you follow this for entire 7 months, definitely I can promise you that you can get a very good score in your KCET chemistry examination. Okay, so yes, so thank you for watching and please subscribe the channel and please join our WhatsApp channel also. The playlist link will also be there in the video, the description section of the video, where you can see the other chapter solutions, electrochemistry, kinetics also. Okay, so with this the physical chemistry of PU2 has completed, and from the next episode we will start with inorganic chemistry D and F block elements. Okay, so please stay tuned for the next episode and subscribe the channel for more such videos. Thank you and see you soon. All the very best for your KCET 2025 preparation.